Okay, this is multivariable calculus, and in this video I'm going to talk about section 14.4, and the topic here is tangent planes and linear approximations. Now, when we go through this section, if you can keep in mind the idea of a linear approximation in two-dimensional calculus, it'll make what we're doing in this section very, very simple, because what we're going to do here is now we're going to start looking at primarily three-dimensional functions, and we're going to start looking at a plane, taking the equation of a plane to approximate the value of a function for points that are close to some point of tangency. So if you take a look at this graph here, this gives you an idea of what we're doing. We have a curved surface here, and we're finding the equation of the tangent plane, and what we're saying is close to the point of tangency, the tangent plane is going to behave in a way very similar to the actual function itself. And just like when we did linear approximations, we would say close to the point of tangency, our function is going to behave similar to the equation of a line. So now we're using, in three dimensions, the equation of a plane. Okay, so keeping that in mind, then it's pretty easy to see where this comes from. So to get the equation of the tangent plane, all I'm going to do is just think about how do I find the equation of a plane, and then we're going to use the partial derivatives in both the x and the y direction to come up with the slopes in the two directions that I need. So the equation of my plane, my tangent plane, is z minus z naught is fx at that point of tangency times x minus x naught plus fy at that point of tangency times y minus y naught. So let's just go through an example of how this works. It says find the tangent plane to the elliptic paraboloid z is equal to 2x squared plus y squared at the point 113. Okay, so remember in calculus BC, we would find equations of tangent lines all the time. And this is really the same idea here. So I'm going to start with my partial derivatives. So my x partial is 4x, my y partial is 2y. And if I evaluate this x partial derivative at the point 113, I'm going to get 4. And if I evaluate this y partial at the point 113, I'm going to get a value of 2. Okay, so in the end, to get the equation of my plane, this is my x naught, y naught, z naught. So it's just going to be z minus z naught. So z minus 3 is equal to my x slope, 4 times x minus 1 plus 2 times y minus 1. And that's the equation of my plane. And we can write this in different forms. You might see it written like this. Z is equal to 4x plus 2y minus 3. So just like when we did equations of lines in two dimensions, sometimes it's nice to have the equation of the plane in this form, because then I can still see where my point of tangency is. As soon as I convert over to this form, I've lost all of my reference to where that point of tangency is. So when you're finding your solutions, really just match the form that you're seeing, whether it be in the textbook, whether it be a multiple choice question. But it's when it's a free response question, I would prefer that you give your answer in that circled form, because that's going to give us reference to that point of tangency, and that's going to give us a better idea of when the plane is going to give us a somewhat accurate representation of the function that we're trying to approximate. Okay, so here's the idea of just the whole thing that we talked about with local linearity in two dimensions. We have sort of the same idea in three dimensions. So the curved surface here is my function, and you can see we've got a tangent plane drawn in there. And all we're doing here is just zooming in on the point of tangency. So as I zoom in on the point of tangency, you start to see that that curved surface looks more and more like a tangent plane as I get closer and closer to the point of tangency. And if I kept zooming in, eventually my curved surface would appear to be almost exactly a flat plane, even though in reality we're zoomed in so far, we're getting a little bit distorted view of what's happening. But the idea behind that is when I'm close to my point of tangency, my tangent plane is a good approximation to the values of my function. Now, the whole idea of being close to the point of tangency is dependent on a lot of things. How quickly your function is changing direction being the primary decider of how accurate your solution or your approximated solution would be. All right, so let's take a look at now linear approximations. So I already pretty well explained what we're doing here. When we do a linear approximation, we're just taking that tangent plane, and now we're going to say, okay, let's treat our tangent plane as if it's a good representation, a good simplified representation of our function. And all we're going to do is just solve for z, and that gives us our linear approximation. So you can see here the exact same thing that we just had with the z naught moved over to the right-hand side. So just like in 2 dimensions when we found the equation of a tangent line and used it to do a linear approximation, now in 3 dimensions we find that tangent plane, and then we use that to find our linear approximation. Okay, so this is pretty easy to do. There's some stuff on here about just different ways this can be written. We can write it in function notation, but still the same idea is going to apply. If you notice here, we've got this thing that's sort of written as our tangent line approximation or our linear approximation. But the reality is all it is the tangent plane with that z naught value moved over to the right-hand side. So you don't really have to memorize a separate linearization function if you know how to find the equation of the tangent plane. All right, so let's take a look at an example here. So this problem says, let L of x and y denote the local linearization to this function, square root of x squared plus y squared, at the point 3, 4, and compare the error in approximating f of 3.04, 3.98 by our linearization with the distance between the points 3, 4 and 3.04, 3.98. Okay, so we're going to go through the steps here, and some of that stuff at the end with comparing to the distance, I'll explain that when we get to it. So the first thing, though, is I need my x partial derivative, which in this case is just x over the square root of x squared plus y squared. My y partial would be y over the square root of x squared plus y squared. And now what I want to do is I want to evaluate my x partial at the point 3, 4. And when I plug that in, I'm going to end up with an x partial derivative value of 3/5. I'm going to get my y partial evaluated at 3, 4, and that's going to give me a value of 4/5. So that's everything that I need for the equation of my tangent plane, which will give me my linearization. So I'll just skip straight to the linearization function since that's what they asked for. My linearization, remember we would have had that z minus z naught. Well, the z here would have been 5, so we would add the 5 over to the other side. So we're going to get 5 plus 3/5. Our point of tangency is 3, 4, 5. So it's x minus 3 plus 4/5 times y minus 4. Okay, so that's my linearization. Now, they want us to actually use this linearization and just sort of assess the accuracy of it. That's really what they're getting at here. So when we plug into this, if I were to go through and say, all right, f of 3.04, 3.98, that can be approximated by that linearization with 3.04, 3.98 plugged into it. I'm not going to plug all the values in. You can do that on your own if you'd like. But when I plug that in, I get 5.008. Okay, so let's look at the actual value. Well, if I actually find f of 3.04, 3.98, so that means I'm actually plugging in to that original function. What I get is a value of about 5.00819. Okay, so you can see my approximation value is pretty close to what the actual function value is. So my actual error here would be about 0.00019. Okay, so that's my actual error. Now, what they wanted us to do is compare it to the distance between the points. Well, the distance between the points, I'm just going to write it up here. My distance between my points would be the square root of, these are the 2 points they're talking about, 3.04, 3.98, and the 0.34. So the difference in the x's would be 0.04 The difference in the y's would be negative 0.02 or 0.02 squared. So that distance turns out to be approximately 0.045. Now, if I compare this error to that distance, what you will see is that my error is less than 1/200th of the distance. Okay, so the reason that we're evaluating that way is we're kind of saying, okay, how far did we move away from our point of tangency, and how much error did that result in when we moved that far? So you can see that even though we moved a distance of 0.045, we got very little error because it's only 1/200th of the distance. So it's just a good way for us to reference the move that we made versus how much error we're getting in our approximation. So you may or may not see that type of error calculation down the road, but I just wanted you to see that there is a way that we can kind of quantify these errors. We can just look at what's the actual error. We can look at percentage error. We can compare our error to the distance between the points. There's a lot of different ways to reference the error, but this one gives us a good overall feel for how far off we are based on the method that we used. Okay, so next thing we're going to talk about here is differentiability. We talked about this a little bit in the last section when we were talking about partial derivatives. But the idea of differentiability here, the main thing that we're looking for when we're looking for is a function differentiable at a point is, do all of the partial derivatives exist at that point? Are there values at that point? And if they exist at that point, that means our function is going to be differentiable at that point. Remember, continuity is not a requirement when we're looking at differentiability for a multivariable situation. Okay, so first of all here, let's look at this question. It says, show that f of xy is equal to x e to the xy is differentiable at 1, 0, and find its linearization there, then use it to approximate f at 1.1, negative 0.1. Okay, so let's take a look at the differentiability piece of this. If I got my x partial, it would just be e to the xy plus xy e to the xy. If I evaluate that at the point 1, 0, I get a value of 1. Okay, so I have an x partial. If I get my y partial, it's actually equal to x squared e to the xy. And if I evaluate that y partial at the point 1, 0, I'm going to end up with a value of 1. Now, both of my partial derivatives exist at that point, and I know that these partial derivatives are continuous because I don't have any points where e to the xy is going to fail to exist. I don't have a rational function. There's no issues here with the partial derivatives being continuous, so I know this is going to be differentiable at that point. So that's what I would state here, because fx, my x partial, and fy are continuous. That means that f of xy is differentiable. And we're talking about at the point 1, 0. Okay, so pretty simple to define differentiability. Most of the function we're going to deal with are going to be differentiable. We're not going to deal with a bunch of things where we have the derivatives not existing at points. Okay, so now it said use this to approximate f of 1.1, negative 0.1 using our linearization. So our linearization here, I would need to know what's the z value or the function value when I plug in the point 1, 0. And when I plug in 1, 0, you can see you get a function value of 1. So that means if you think about your z minus z naught, it would have been z minus 1. So we're going to add that 1 to the other side. So we get 1 plus my x partial times x minus 1 plus 1 times y minus 1. Okay, so there's my linearization. And in the end, I can simplify that down. That's just the same as x plus y. And it simplifies down to x plus y because we had the 1 here. We're going to get a negative 1 out of that. So those are just going to cancel out and we just get x plus y. And so in the end, if I want to approximate my function, f of 1.1 negative 0.1, it's going to be approximately x plus y, which would just be 1.1 minus 0.1, and so it's going to be approximately 1. Okay, so the whole purpose of using these linearizations is that we're trying to do the same thing that we did in 2 dimensions. So we're starting off with just a tangent plane approximation that will sort of be like the most basic type of approximation model that we can use. But there is actually a Taylor series in 3 dimensions, and we can create those. It's way beyond the scope of this course because it gets into linear algebra, but this is the most basic Taylor series model that I can use in a multivariable setting, is using the equation of a tangent plane. But realize, just like when we did Taylor series in BC calculus, and we would start talking about quadratics or cubics or quartics, and that would allow us to go further from our point of tangency, we can do the same thing in a multivariable setting. We can create a Taylor series that allows us to go further from our point of tangency and still have an accurate model. But like I said, it's well beyond the scope of this class, but the same ideas do still occur in 3 dimensions as what we saw in 2 dimensions. All right, so last topic I want to talk about here are differentials. So differentials we've talked about before, again in 2 dimensions, and it's sort of the same thing here. What we're doing is, it's instead of expressing these changes in the values like z minus z naught or x minus x naught, we're just going to represent them as differential expressions. So if you look at this differential dz, this is the exact same thing as the equation of the tangent plane written in a slightly different form. So that's all we really are looking at. So when we talk about a differential, though, remember that the dx and the dy now are going to be our actual changes, and then the dz is going to be our approximated change in our z value. So the dz and the delta z are not necessarily the same. You can see over here. And again, if you think back to linear approximations in 2D, this is the same idea. So I know that the differential value and the delta value are typically not going to be the same. And that's because, remember, dz is an approximation of how much my function is changing. It's not the actual change in the function value. Okay, so let's take a look at how we can use this. So it says approximate the change in z equals y squared from its value at 0.51 to its value at 0.503, 1.004. Compare the magnitude of the error in this approximation with the distance between the points 0.51 and 0.503, 1.004. Okay, so let's take a look at how we would do this. So first thing we need is our setup here. So dz is going to be given by, remember, the x partial derivative, which would be y squared here, times our change in x, plus the y partial derivative, which would be 2xy, times our change in y. Okay, so I'm sort of skipping through the steps there, but I think you get the idea. It's just the change in z is equal to the x partial times the change in x plus the y partial times the change in y. So now let's actually evaluate here. So dz, let's see, dz, when I use that point 5.03, 1.004, remember our change in z is going to be approximated by this. So our original y value was 1. The change in the x, we went from 0.5 to 0.503. So that's a change of 0.003 in the x direction. The change in y, first of all, I have 2 times my x was 0.5, my y was 1, and my change in y is 0.004. So what we end up with is an approximated change in the z of 0.007. All right, so let's take a look at the change in z, the actual change in z. So the actual change in z would be 0.503 times the 1.004 squared. All I'm doing is using that function. And then I would subtract away the 0.5 times the 1 squared. And what that gives me is roughly 0.007, but then I get a little more accuracy, 0.03 0.2048. So we could write as many decimals as we want, but you can see that the approximated change in z is pretty close to the actual change in z. So my error here is just the difference between the two of those. So delta z minus dz, and if I subtract that out, you can see that we're going to get 0.000032048. So that's my actual error. Now, just like that one that we looked at earlier, we can get the distance between the points. If we find the distance between the points 0.5 and 0.503, we'll find that distance to be about 0.005, and actually it's exactly 0.005. So that's how far those 2 points are apart. So if I compare my error to that distance, well, that error, let's see, I'll just do the error over the distance. So my error over the distance is that 0.000032048 divided by my distance of 0.005 is about 0.0064. And so what that means is my error, if I just want to put it in terms of like a rational number, it's less than 1/50th or 1/150th of the distance. And that's the distance between the points. So again, just another way of referencing that error. Instead of just having this general error where I don't really know what that means because I don't really have a reference to how far I moved. Now I'm comparing, okay, compared to how far I moved, you know, a very small distance, but my error was only 1/150th of that distance. So it's relatively small error. All right, so we've got some more problems here, and I'm going to have you try some of these, and then we'll just talk about the solutions. So the first one says if z is equal to f of xy is equal to x squared plus 3xy minus y squared, find the differential dz. And if x changes from 2 to 2.05 and y changes from 3 to 2.96, compare the values of delta z and dz. And for the error this time, I just want you to find the difference. So you can pause the video, and when you come back, I'll show you the solution. Okay, so here's what you should have come up with. So my dz, or my approximated change in z, is my x partial times the change in x plus my y partial times the change in y. Then we just plug the values in, and you can see here that we get a value of about 0.65. And then I'm going to find the actual change in z. And you can see now these are pretty close together. But in terms of actually calculating it out, you get an error of about 0.0051. And again, without having anything to reference that to, that error sounds really good. But what's more helpful is when we have something to reference into, like we did on the last one, if I compare that to the distance between the points, it would give me a general idea of, does this seem like a good error or not? Okay, so let's try this next one. It says the length and width of a rectangle are measured with errors of at most 3% and 5% respectively. Use differentials to approximate the maximum percentage error in the calculated area. Okay, so I'm going to help you with the setup, and then I'm going to have you finish this one out. So first of all, I'm just going to say my area is xy. Okay, so from the perspective of the dx this time, my change in x is going to be the amount that x can be off. And it says my error is at most 3%. So when we're talking about 3%, we're talking about 3% of x. Same thing with the dy. We're talking about 5%. We're talking about 5% of y. Okay, so use that information, try to set this one up and solve it out. And after you unpause the video, I'll show you the solution. Okay, so here's what you should have come up with. We've got our x partial and y partial. We've got our differential dA. And so you can see I did my x partial times dx plus y partial times dy. And it ended up simplifying down into this equation that I have here. And this equation is 0.08xy. Okay, so then from that, how do I figure out what my maximum percentage error is. Well, my dA is 0.08 xy. Let's divide that by our area. And when we divide that, notice the area cancels out and we end up with 8%. So it sort of works itself out in that case where we were able to get a percentage of the area because everything canceled out. If we wouldn't have had such a simple function, it's possible that the xy wouldn't have canceled out and we would have had 8% of something. But in this case, it all canceled out very nicely. Okay, last question. This last one, it says the dimensions of a rectangular box are measured to be 75, 60, and 40 centimeters. Each measurement is correct to within 0.2 centimeters. So we don't have any percentage errors this time. We have an actual tolerance of measurement of 0.2 centimeters. Use differentials to estimate the largest possible error when the volume of the box is calculated from these measurements. So I want you to go ahead and try that out and see what you can come up with when they talk about the largest possible error. Remember, we're talking about the error in the volume measurement. So pause the video. When you come back, I'll show you the solution. Okay, here's what you should have ended up with on that one. I use just X, Y, and Z. Doesn't really matter what you use for the variables, but I have my volume as X, Y, Z. And so now I did my approximation. Now we have more variables this time. Same process still applies. So I did the X partial times the change in X, the Y partial times the change in Y, and the Z partial times the change in Z. So I have that third term that we hadn't really seen before, but I can expand this out to as many variables as I want. And then from there, we're just plugging in the values. So we find dV, and remember, dV is our approximation for delta V. So delta V in this case is approximately 1,980 cubic centimeters. So once you wrap your head around these questions and the idea behind these questions, it's actually very, very simple. The hardest part is typically just the actual calculations that you have to do, because, you know, when you do the partial derivatives and when you're plugging in these values, there's a lot of places to make a mistake. But conceptually, the idea of using these tangent planes and then using them to do linear approximations, I think is so much like what we did with linear approximations in 2D that you'll have a very, very easy time with it.